much for the thank you very much for the invitation. So let me also start my timer. Yeah. So I'm going to talk a bit about part of a project that I have with Rossi Laking and Lang Mo about mutations of infinite dimensional representations that, roughly speaking, consist in extending Derek Sandman and Selevinsky's mutations of finite dimensional representations to the infinite dimensional setting, where the representations are allowed to be infinite dimensional. This is the plan of the talk. So let me start recalling very briefly what are how are quiver mutations defined. To mutate a quiver, so we start with a quiver and a vertex k with the property of not having two cycles incident to k. In other words, the quiver q may have cycles of length, oriented cycles of length 2, yeah. But then the quiver at which we are going to mutate, we take it to be not incident to any such cycles of length 2. And then the mutation in direction k, or with respect to k, transforms q into a two acyclic quiver. So it transforms it into a new quiver that doesn't have two cycles by following these three combinatorial steps. Namely, every time you have an incoming arrow into k and an outgoing arrow from k, one adds a new arrow that one thinks of as a composite arrow from j to I. Then one reverses arrows incident to the mutating vertex. And then finally, one removes two cycles, say one by one. Yeah, so that's what it means. Maximal collection of disjoint two cycles is that you can start looking for two cycles, and then whenever you see one, you erase it. Let's say just combinatorially, and then keep looking for two cycles. If you see another one, you erase it, etc. It is, for technical reasons, important to give some notation for the quiver obtained after applying only the first two steps, namely before removing two cycles from the picture. And this is going to be denoted just mu k tilde of q. So here you can see an example, well-known example. So we take this free cycle with arrows A, B, and C. In the first step, you see there's this incoming, this outgoing, so one adds this composite arrow in the first step. In the second step, one reverses the arrows incident at k, so these arrows get reversed. And in the third step, one looks for two cycles. So here there's one, and one erases them. And here is this quiver that for technical reasons I have to keep track of in the process. Okay, so that's the definition of quiver mutation. Let me remind also very briefly about Bernstein, Gelfand, Ponomarev reflections. Because, yeah, why do I want to recall them? Because if k happens to be a sink or a source of the quiver, namely if k happens to be a quiver, a vertex with the property that no arrows go out from k, or no arrows come into k, then this process of mutation simply reduces to just reversing the arrows incident to k, namely transforming K from a sink to a source or from a source to a sink, and that's it. So, and the Bernstein-Gelfand-Ponomarev reflections somehow are we take them as a guideline of what mutations in general for general vertices should look like. So, oops, I'm sorry about that. Yeah. So when I do it very briefly, when K is a sink, namely in this situation where there are no arrows coming out from K, and one takes a representation of the quiver, yeah, of course, the quiver may have many vertices and arrows in this part, but no arrows coming out from K. Yeah, and so when one takes a representation, one can assemble the linear maps associated to these arrows incident to K that arrive at K. One assembles them, and Bernstein-Gelfand-Ponomarev, what they do is they replace MK with the kernel of this map, yeah, and then they reverse the direction by simply including such kernel into that direct sum, and that's it. And similarly, when K is a source, so in this situation where of course Q may have some more vertices and arrows here, but like no here, and one takes a representation, one can again assemble the linear maps associated to these arrows. And then what Bernstein-Gelfand-Ponomarev do is they replace MK with the co-kernel of this map. Yeah, and then being the co-kernel, one has a projection from this space to the co-kernel, which is a quotient of this space, and that is how they reverse this arrow and make it. They reverse it and transform it into this arrow. Yeah, and then you see what they do in both cases is they replace the vector space that was attached originally to K, and then they reverse the linear maps. Yeah, and then the rest they just keep it the same. So the rest of the representation remains the same. Okay, so that is that's going to be our guideline, to replace with the kernel and with the co-kernel. Yeah? And now we want to do it for arbitrary vertices, namely for vertices that are not necessarily sinks nor sources, and that hence look like around such vertices one has the quiver looks like what you are seeing here. Yeah. If I take any representation of such a quiver, we can still form the linear maps that we formed before, that we assembled, namely the ones associated to this. We assemble them into a single linear map from this direct sum, and we can also assemble all this as a linear map to the direct product, but it's finitely many of them, so it's also the direct sum. Yeah, and then naively we can say, let's try to do exactly what Derksen, Neumann, and Selevinsky do, namely let's try and replace this with something coming from the kernel of this and the co-kernel of this, and then reversing the arrows also by just including the kernel and projecting onto the co-kernel if possible. So the most naive or obvious way to do that is replacing then MK with, well, just the direct sum of the co-kernel of this with the kernel of this. And then obviously then say, okay, from here, let's just include the kernel here and then send the co-kernel to 0. And from here, let's just project onto the co-kernel. Yeah, and then let's not, yeah, that's kind of, let's ignore the kernel for this map. Okay, so that one can do, and then one has the maps attached the linear maps that should be attached to the arrows that are obtained by reversing the arrows incident to K. One still has to associate linear maps to the composite arrows that we mentioned at the beginning. That's also very easy, no? Because if one has a representation of this, one has all these linear maps, and then to the corresponding composite arrow. Let's say in this case is like B1A1 brackets. One can, of course, just associate the composition of those two linear maps. So one has this matrix that represents all the linear maps attached to the composite arrows. So in a way, so far so good. We would only have to take care of how to delete two cycles, which we will say some words a bit later. But it seems like so far so good, right? I mean, kind of the naive approach can be performed, yeah. But there is a problem that if you care about cluster algebras, this approach doesn't work, and it doesn't work because it doesn't give the correct information. So there are some things called cluster algebras, which I'm not defining, yeah. But in these cluster algebras, there are two important notions. One is that of G vector, and the other one is that of G polynomial. And let's say, let me say just briefly, like what is a G vector in a cluster algebra. So there is a type of cluster algebra called cluster algebra with principal coefficients. And in a cluster algebra with principal coefficients, one can define a degree. In other words, such a cluster algebra with principal coefficients is a graded ring, graded by z to the n. And there is a grading with the property that every cluster variable is homogeneous with respect to such grading. And this grading has a couple of other properties. And the degree of a cluster variable is then called the G vector of that cluster variable. So G vectors are degrees of elements in certain ring called the cluster algebra. And F polynomials are defined in a slightly more cumbersome way, so let me not define it. And the point is, if one tries to define a mutation of representations following Bernstein-Gelfand Ponomarev just naively, let's say the injective G vector of the representation one obtains does not behave like the G vector of the cluster variables in the corresponding cluster algebra. And the reason is actually that that this space is way too big. It is too big. So what Dirksen-Newman and Celebinsky thought was, okay, so this is too big, so let's try to just amalgamate them along certain subspace of each of them. This idea, I think, is like a really genius idea from Dirksen-Newman and Celebinsky. And how? Well, what they say is, okay, let's not do it for arbitrary representations, not for arbitrary representations of the quiver, but let's try to do it for those representations that are annihilated by the cyclic derivatives of a potential on the quiver. That is, let's try to define it for some modules over some quotient of the path algebra or the complete path algebra of the quiver. Okay, so what is a potential? A potential is a potential on the quiver is a linear combination of cycles of the quiver. And for technical reasons, one has to allow it to be maybe infinite. So a possibly infinite linear combination. So maybe it's an infinite sum of cycles of the quiver. Okay, now given a potential on the quiver, one can define for each arrow of the quiver a cyclic derivative of the potential with respect to the arrow. And I'm not going to give the precise definition, but very roughly, the idea is that with the potential at hand, the cyclic derivative with respect to A is a linear combination, possibly infinite, of paths that go in the other way, in the opposite direction. So paths that go from the head of A to the tail of A. And there is a precise definition that I'm not writing down. And there is such a cyclic derivative of S for each arrow. So there are as many cyclic derivatives as there are arrows in the quiver. And the Jacobian algebra is, well, let's say, one would like it to be just the path algebra of the quiver, modulo the ideal generated by all the cyclic derivatives. Now, for technical reasons, that doesn't quite work. That's not quite the correct setting. One has to take the complete path algebra of the quiver, whose elements are all the possibly infinite linear combinations of paths. And from there, one mods out a certain topological closure of the ideal generated by the cyclic derivatives, where this the topology is the M-adic topology. You know, the open neighborhoods around 0 are simply the positive powers of the arrow generated by, sorry, of the ideal generated by the arrows inside the complete path algebra. So as an example, let's say here, this is a quiver with potential. So here, of course, the potential, I'm calling it S tilde. Yeah, but it's anyway a quiver with a potential. The cyclic derivatives tell me, I know that I didn't give the precise definition of cyclic derivative, but if one follows the precise definition, one obtains that the Jacobian algebra of this quiver with potential is this complete path algebra modulo this relation. So BC is 0, CA is 0, C actually is 0, but D is equal to AB. So you see here, this tells me you could in principle actually just delete C from here because C in the quotient is 0. But you cannot, strictly speaking, delete D because D is equal to AB. Okay, but however, at the level of representations, if you think about the representation of this quiver, if one wants to give a representation of this quiver where this equality D equal to AB holds, one only has to give the linear map corresponding to A and the linear map corresponding to B. And then the linear map corresponding to D is forced. So one doesn't need it as an input information. So and this suggests that somehow one should be able to delete D because D is kind of the action of D is not something we need to give for a representation, but one can deduce it from the actions of A and B. And then the formal way to do it is provided by Dirksen-Neumann and Celebinsky's splitting theorem, which what it does is in order to be able to delete D and not only C from the quiver, one applies certain automorphism of this complete path algebra by sending D to, and actually here the rule is very explicit, is D goes to D minus whatever appears with C here. So it's plus AB. Yeah. Anyway, this defines an automorphism of the complete path algebra, and also induces an isomorphism of Jacobian algebras. And in the new Jacobian algebra, one can easily see that D is also zero because it is equal to the cyclic derivative of C of the image of S tilde under the automorphism. Okay, so this Jacobian algebra turns out to be isomorphic to the Jacobian algebra of this type A3 quiver with a zero potential. And this is developed very systematically by Dirksen, Neumann, and Celebinsky. Yeah? So kind of the moral I want to extract from this is that if one has two cycles in the quiver, then if you choose your potential correctly, you may be able to delete the two cycles from the quiver in the end, and to do so, or you may need to apply an automorphism of the complete path algebra. Yeah? And it is for this for such procedure to always produce an automorphism of the algebra, that one needs to work with complete path algebras and not only path algebras. So to ensure that one always obtains an isomorphism, and hence also an isomorphism that then allows you to delete two cycles. So that's Dirksen, Neumann, Celebinsky's splitting theorem in a nutshell. Okay, but let's go back, because we were interested in mutating representations, right? So we already introduced cyclic derivatives, yeah? And so to be able to mutate representations, representations of what? Of the Jacobian algebra, some modules over the Jacobian algebra, we also need the notion of second order cyclic derivative. Yeah, which works as follows. Given a quiver with potential and a path of length 2, one defines the second order cyclic derivative with respect to that path of length 2. Yeah, it has a specific definition, which is very similar to the definition of first order cyclic derivative. I'm not going to give it explicitly or precisely. I'm just going to say that it follows the same principle, that you have your path of length 2, and the cyclic derivative of S with respect to that path is a possibly infinite linear combination of paths that go the other way around. So from the head of the two path to the tail of that two path. So that's how this possibly infinite linear combination goes. Now, given any representation of Q, we actually any module over the complete path algebra. But for simplicity, just take already a module over the Jacobian algebra. We have linear maps. Well, given such a path of length 2, we have, of course, the linear maps associated to such arrows. Yeah, but also the second order cyclic derivative being an element of a linear combination of paths, it also acts on the representation. And how does it act? Well, it acts through certain linear map. So we also have this linear map, from the tail from the head of the two path to the tail of the two paths, so in that direction. Okay, so we have that. Yeah, we can assemble, and as before, we obtain this incoming map, this outgoing map, and now we can assemble all these maps going from the heads to the tails that then go this way. And these are all those linear maps. Yeah. And now, if M is actually a module over the Jacobian algebra, it is in particular annihilated by the cyclic derivatives. Yeah, and this can be easily seen to imply this equality, these equalities, that alpha gamma is 0 and gamma beta is 0. In other words, this composition is 0 and also this composition is 0. That's what this means. Yeah? And of course, this means that the image of gamma is contained in the kernel of alpha, and that the image of beta is contained in the kernel of gamma. Okay, this if M is a module over the Jacobian algebra. Yeah, but in that case, then we have the following. So of course, we have the inclusion of the image into the kernel of alpha. Yeah, and because of this containment, we also have that gamma induces a linear map that goes out from the co-kernel of beta. There's an induced map because of this. Yeah. Okay, and then if we choose a section for this map, we notice then that we have image of gamma as a subspace of kernel of alpha and of kernel of beta. Yeah. Of course, such a section is not canonical. Yeah? But if we take one, we are choosing a way of seeing the image of gamma as a subspace of this. Okay? Which is what we said, right? Try to amalgamate this space with this space along a common subspace. And this is the genius idea of Derksen, Neumann, and Celebinsky. They say, okay, do that. Amalgamate along that image of gamma. Yeah? Of course, you have to choose what potentials you are going to work with. Yeah, but somehow you have a lot of freedom, because there may be at least one potential that does the job in terms of cluster arguments. Yeah, and those are the so-called non-degenerate potentials of Derksen, Neumann, and Celebinsky. Okay, but now how does one mutate the representation given this information? So that is assuming that M is a module over the Jacobian algebra of QS. Well, now we can amalgamate these two spaces along the kernel of alpha. So I'm writing it this way. Yeah. So you can check that this is isomorphic to the co-kernel of beta. So yeah, so this is isomorphic to the co-kernel of beta, whereas this one is isomorphic to the kernel of alpha. Yeah. So you have there the kind of the amalgamation. Yeah. And then what they do is they say this space simply include it here as before. Yeah, and that's what you are seeing here. And I'm not going to go into details there, but this map, that's what it does. It includes the kernel of alpha here. Yeah, and then they say from here to here, well, ignore this part, that is the part from kernel of alpha that is not involved in the amalgamation. Yeah, so ignore it. Yeah, and then project from here to here, well, with a minus sign. So they put a minus sign, and that minus sign is kind of just to make things work nicely in terms of a new mutated quiver with potential. Yeah. And the composite arrows, well, still take the obvious ones. The linear map for the linear maps for the composite arrows. Okay, and then they prove that if M is finite dimensional, then this defines so let me backtrack a little bit. Yeah. So you see, with this information, what we have is linear maps attached to the arrows of the quiver mu k tilde of q that I mentioned at the beginning of the talk, before deleting 2 cycles. And having those linear maps attached to the arrows of these quivers amounts to having a module over the path algebra. But for technical reasons that have to do with the removal of 2 cycles, one really needs a module over the complete path algebra. So that's what they prove, that if M is finite dimensional, then this information that gives you a module over the path algebra can be extended to a structure of module over the complete path algebra. Yeah? And it's annihilated by the Jacobian ideal of certain new potential that I'm not going to write in detail, but that is a very specific potential that, of course, is defined in terms of S. Okay. And what they do is they define, this so-called pre-mutation, because somehow one has not yet deleted 2 cycles. Then what they do is, okay, with the process of 2 cycle deletion that I gave you in a nutshell some minutes ago, just take the module that you have, yeah, and then somehow the action of the mute of somehow just forget the action of those arrows that you can get rid of with the deletion of 2 cycles process that I mentioned. I know that it's a little bit of a mouthful, but yeah. And so they define a mutation, yeah? With the only caveat that depending on which potential you started with, it may be that in the new Jacobian algebra there may be 2 cycles that cannot be removed. You know? And this depends on whether the potential is non-degenerate or not, for example. Okay, so they define mutations of finite dimensional representations. And they actually, I mean, and then they prove that these mutations of finite dimensional representations, if your potential, if your original potential was non-degenerate, then it gives you the correct cluster algebra information. So somehow the G vectors that you form with injective co-presentations of finite dimensional representations, they give you the correct G vectors of the corresponding cluster variables. Okay, now here what you are seeing is an example, which is actually, this quiver with potential, just the 3 cycle with S is actually the 3 cycle itself, and you have the projective at 3 of the Jacobian algebra, and here is like the whole information that one like kind of the mutation process that I described earlier here. And the final answer. Yeah? So in this example, that for time reasons I don't stop to describe in full detail, you can see that the mutation of this projective at 3 is the projective at 3 over the new quiver with potential, over the mutated quiver with potential. Okay. Now mutations for infinite dimensional representations. Like first is why would one want, or why would one be interested in being able to mutate those? The first one is that, as was just hinted here, is you see mutation of P3 was P3. This is actually something that holds in general for finite dimensional projectives and injectives. Namely, if you have your Jacobian algebra, and you take an indecomposable projective which happens to be finite dimensional, and you mutate it with respect to a vertex different from the vertex at which the projective is projective, you obtain the corresponding projective. And the same thing for the injectives, as long as you take an indecomposable finite dimensional injective. The Elf dimensional, the Elf finite dimensional injective goes to the Elf finite dimensional injective as long as you are mutating at a different vertex k. Okay. But now there are nice quivers with potential. And nice, I mean that, for instance, this is non-degenerate in the sense of Derksen, Neumann, and Celebinsky, and hence is good for cluster algebra purposes, whose projectives are infinite dimensional. Yeah, and Derksen, Neumann, and Celebinsky don't tell us how one can mutate them. And actually this situation happens actually for many triangulations of punctured surfaces. So there are many triangulations of punctured surfaces that give us non-degenerate quivers with potential with infinite dimensional indecomposable projectives. So one would like to at least mutate those because they arise from good quivers with potential. That's one thing. That's one reason why one would like to mutate infinite dimensional representations. Another one is that if you take an unpunctured surface and an arc in that unpunctured surface, then given any triangulation of the surface, the Jacobian algebra is gentle. Yeah, and the arc induces a string on this gentle Jacobian algebra, and hence a string module. And this happens for any triangulation. So if you fix your arc, then for any triangulation, you have a corresponding string module for that gentle Jacobian algebra. And something I proved many years ago is that if you have two triangulations now that are related by a flip, then the string modules that you associate to them are related precisely by the mutation of representations of Derksen, Neumann, and Celebinsky. Yeah. Okay, and then you can say, yeah, but these are finite dimensional, right? I mean, this string module is finite dimensional, or the band module if gamma is a simply closed curve. Yeah. Here you are seeing an example of such of this theorem, where one fixes a curve, which is this one, yeah, and then takes two triangulations related by a flip. Yeah, and actually this example is actually, you see, P3 that goes to P3, yeah, on their mutation, but also if you just read the string. Yeah, so this is an example of this that I proved in my PhD. Yeah, okay, but then again you can say, yes, but these are finite dimensional. Yeah, now the point is that you can also do you can associate certain infinite dimensional string modules to certain curves that are no longer arcs but kind of asymptotic arcs. Kind of, they are in a way kind of not compact, right? As in the work of Bauer and Laking, yeah, where they work over annuli with points on their boundaries, yeah, and no punctures, yeah. And then, for instance, here you are seeing this non-compact curve that somehow at some point is just kind of starts, accumulating in some closed curve. Yeah, and you have this triangulation. Yeah, and here you have the same curve, the same non-compact curve, but you have a new triangulation, namely from this one, we flip this arc. Yeah, so we obtain this. Okay, and for each one, you have, well, here the gentle Jacobian algebra and the representation that Bauer and Laking associate to the curve representation of this algebra. Yeah, and here the corresponding the same construction, but for the new Jacobian for the Jacobian algebra of the new triangulation. Yeah. Okay, so you can certainly do this and this. And now the question is, okay, but what is the relation between these representations? Right. So hopefully it's also that the relation between them is also a mutation, like in this case, like in the finite dimensional case. Okay, okay, so we have at least two motivations. Right? So we would like to at least be able to mutate the projectives when they are infinite dimensional, and also certain infinite dimensional representations that also arise very naturally from curves on surfaces. Okay, now how do we do it? Now take any module over the Jacobian algebra. Yeah, infinite dimensional or not, I no longer care. Yeah, we can still assemble maps as before, the incoming map, the outgoing map, and the map arising from the second order cyclic derivatives. Yeah, being a module over the Jacobian, that this is satisfied. Yeah. So one still has this. So choosing a section here, one can still amalgamate this space and this space along this common subspace. So we do that. Right? So one simply does that. Yeah, and then arises at the same picture, right? So where from here to the co-kernel, one takes minus the projection and ignores this part of the kernel of alpha. And from the kernel of alpha, one just includes into this space, and this is mapped to 0. Yeah. Now, as I said before, this defines a representation of the quiver mu k tilde, namely a module over the path algebra of mu k tilde. So the path algebra, not the complete one. Yeah, and now, well, fortunately, this action of the path algebra on this representation extends to an action of the complete path algebra. So one can actually make this into a module over the complete path algebra, and it is annihilated by the Jacobian ideal of this potential. So one can define the mutation. The mutation is defined. Okay, so one can indeed do it, following the same guidelines of Derksen, Weyman, and Selevinsky. It's just that maybe they didn't notice that if M was infinite dimensional, then this action could be extended to an action of the complete path algebra. Okay, example. So here you are seeing the representations that you saw before that arise from the work of Bauer and Laking, that you see that were associated to these non-compact curves that spiral. Yeah, and then if you take this one and mutate it with respect to the vertex, which was the arc that we flipped in the triangulation. Yeah, and then here is the process. What you obtain is this, which is yeah, sorry, it is isomorphic to the one they define, because here one has to put a minus sign, but it's isomorphic to the one that Bauer and Laking define. So that is, these are those infinite dimensional representations from the work of Bauer and Laking. They behave well, yeah, under this mutation of representations. And moreover, now now it doesn't matter if the projectives are finite dimensional or not; they are well behaved. Yeah? Of course, as long as you still mutate at a vertex different from the vertex at which you are taking the projective. Yeah? Okay, and also the nilpotent, the injectives, but the locally nilpotent injectives, which here is the definition. Is you take the injective envelope of the one-dimensional simple at the given vertex, yeah, but that injective envelope, you take it not in the whole category of modules, but only in the category of locally nilpotent modules, where a module is locally nilpotent if for every vector in the module, there is a sufficiently long length with the property that every path longer than this length annihilates this vector. Yeah, and of course, locally nilpotent means that maybe if you let the vector vary, the index of nilpotency may be unbounded. Yeah, but at each vertex, at each vector, you have nilpotency. Okay, and the pictures you are seeing here are actually, they are pictures of the projective or the projectives for the quiver with potential that we saw before, which arises from one puncture torus, and here is like the torus drawn but on the plane, but I'm running out of time, so I cannot stop to give more details. But the point is here you can see that the projective for each also arises from a given curve, which is the same curve on the torus in both situations. So somehow this is consistent with the previous example that I gave you. Okay, and maybe I'm running out of time. So in the composable projectives are well behaved under this mutation of infinite dimensional representations. The locally nilpotent injectives are well behaved, and also the pure injectives. Yeah, so here is the definition of a pure injectivity of what is a pure injective module. And they are, again, the mutation of a pure injective is pure injective. And something we are working on is this mutation of infinite dimensional representations. Now we know that it sends pure injectives into pure injectives. Now what we believe is that it is actually a homeomorphism if on the set of pure injectives you put the Ziegler topology. And yeah, and I ran out of time, so I think I'm going to stop there. Yeah, there are some more modules that are well behaved, but I think since it was a 15-minute talk, I prefer to just stop. Yeah, thank you.
Well, thank you very much for your very nice talk. Thank you. Are there any comments or questions? So let me start with a small question. What about the mutation of the stilting modules?
Can you say it again about the
Silting object.
Yeah, this
Because I know, for example, Rosanna and Lydia also they will try to mutation, but in by using just some technique of the large model category. I mean, not only just by the. I mean, in a covariate potential, if it is possible to mutate.
Yeah. So this is something that it's still, you know, on the to-do list, but somehow the what we would be proving is that mutation of co-silting is co-silting. And actually, mutation of a co-silting pair is a co-silting pair. Right. But you see, it goes kind of transversally to the way that Gideon Geleri and Rossi mutate co-silting because they take an associative algebra and then and actually a finite dimensional associative algebra, but okay, whatever. But they mutate co-siltings in that, you know, over that algebra. Yeah, and what we are doing is we are going to a new algebra, which is the new Jacobian algebra. And now we are mutating the objects from here to this one. So it's kind of transversal, similar to, you know, like to Adachi Yama-Reiten, who they have this Adachi Yama-Reiten mutation, which mutates tau tilting to tau tilting, but over the same algebra. Yeah, and actually, Derksen, Neumann, and Selevinsky, they show that mutation of tau tilting is tau tilting over the new algebra.
Yes.
Yeah. So somehow what is in the to-do list for us still is this what I just said, but for co-silting pairs.
And so maybe after that, it is possible to connect the co-silting objects in the algebra, means Jacobian algebra, and the mutation of the co-silting objects in the mutation of this algebra.
Right. Yeah. Because yes, because you would automatically have yes, you would automatically have commutativity. Yeah, that if you have two things here related by a Angeleri-Laking mutation, then on the new one their mutations here, they are also related. Yeah, kind of exactly like what happens in tau tilting.
It's very nice. And so we have a Hesse-Quiver here and Hesse-diagram here equivalently.
Yes, but one has to be careful because the partial order actually changes. Not the same partial order. Yeah. So let's say just at the level of unoriented graphs.
Yeah. Thank you. And other question about the cluster algebra. In a one joint work with the Karin, we show that for some cluster algebras, the cluster algebra generated by the projective cluster variables, which means that the cluster variables which correspond to the projective objects in a cluster category.
Yeah.
And now you show that in a Jacobian algebra, the projective mutation of projective is the projectives.
Yes.
The question is that, for example, if you start with algebra, means Jacobian algebra, such that the corresponding cluster algebra generated by projectives, then they mutate this algebra and also mutate these projective cluster variables. So we have all projective cluster variables in new algebra. And what about the subalgebra here generated by this projective cluster algebra? I mean, it's equal to whole cluster algebra, or is it proper subalgebra?
But you mean, 1 second. Yeah, this I don't know. I'm a bit confused now. Yeah, because let's say yeah, somehow my question is, how do you define the cluster variable associated to the projective? Do you define it as the Calderon-Chapoton function?
Yes.
Of the projective,
it's a denominator corresponding to the dimension vector of the indecomposable projective of the quiver, the corresponding path algebra.
And okay, but then yeah, okay, just one question then. But then do you work with the quiver Grassmannians of quotients of quotient representations?
Yes, it's a covalent representation.
Okay, because in that case, yeah, because first of all, you need to assume the projective to be finite dimensional to indeed land in the cluster algebra. And second,
yes,
I think
yes.
Yeah.
In our case, projectives are finite dimensional.
Yeah, okay, and in that case, I think then the answer is no, that it's not equal to the whole cluster algebra, because and I think one second. I'm getting a bit confused. Yeah, sorry. I'm a bit confused. Sorry.
In some cases, it's true. For example, we prove for case A and case D. If we start with the quiver of type A or D, and then calculate the projective cluster variables, and then the projective cluster variables generate the whole cluster algebra. And also, if it mutates the quiver in one of the vertices, again, in a new quiver, the same is true. The projective cluster variables of the new quiver also generate the new cluster algebra. But my question was some other example, for example, for gentle case or some other.
Yeah, I mean, somehow I would say that, I mean, if you take this quiver, but not with this potential, but with the potential which is this plus A1 B2 A1, sorry, plus A1 B2 C1 A2 B1 C2. I think for that one, what you say is not going to hold.
Yes, we have also some example which is not the whole, but I mean, which kind of the cluster algebra
I
we
see.
have the
Okay,
whole.
okay. Yeah, this okay. Yeah, I think at the moment I don't quite know. Yeah, yeah, sorry.
No problem.
I mean, I'm tempted to say, but I'm not sure. I mean, I don't really know, but I'm tempted to say that when you have um, a punctured surface with a non-empty boundary, and let's say at least 2 mark points on the boundary, I'm tempted to say that for those it is true, but don't quote me. I mean, take it with a grain of salt. Yeah.
Thank you. Just the idea.
Yeah. And so sorry that
No, thank you very much.
I also got a bit confused. Yeah, just sorry.
No, thank you. Are there any questions or comments? So if not, let's thanks Daniel again. Thank you very much. Thank you for your nice talk.
Thank you for the invitation.